So this is the topic, transformation of random variables. This is a very simple topic, and you have already seen it in many places. So you have a random variable z, which you want to transform into another random variable x. And this is how you do it. Here, z is a simple random variable, let's say simply a uniform distribution, and how you transform it into x. This is the rule. Let me do it again in our today's class. Let us begin. So let's say there is something, I'll give some other notation, maybe u and x. So you have some simple random variable u which you want to transform into x, right? So your random variable u has some distribution puu. Okay, let me use the notation that capital U. Let's keep it small only. It's basically a random variable. So puu. Just a minute. Let me be consistent with my notation. Okay, I think it's all right. I will use small only everywhere. Generally, people use capital U to denote the random variable and the small u for one particular sample from that random variable. But in this case, I'm just using small u for both. So puu means u is the random variable and it has a distribution p, and this u is a particular value, and so that this function gives you a scalar number, right? So let's say pu could be just a uniform distribution 0 to 1. Then my puu, where this particular u can take these values from 0 to 1. If this particular u is 0.5, what is the value of the puu? Yes. What is this value?
1.
1. Very good. So actually all of these, so you can take any value. For all of these values, the value will be 1. The value of puu will be 1 if u lies between 0 to 1, and beyond this range it is 0. Okay. So this is a simple uniform distribution. But if I apply some transformation, let's say I apply a transformation, let's say my x is equal to 2u plus 3. Then what will be my pxx? How will this look like? Yes. How will this look like? X is basically some transformation of u, and in this case, this is 2u plus 3. So how will my pxx look like?
The distribution will now start from 3 and end at 5, and it will remain uniform.
Yes. What's the value?
This would be half.
Very good. So that the sum of the area under this curve should be 1, right? I know my pxx dx is equal to 1, right? And you can also use the transformation of random variables to derive this. How will you do that? Pxx is equal to puu times yes, du by dx mod, right? And this you will compute for a particular u, right? You compute this for So see, you do not know you only know your x, right? Let's say your x is 2 or x is 2 or x is 3.5 something. You know x, you don't know u. So basically you have to compute this whole thing at u equal to t inverse of x, right? So what is my u? What is my u is to inverse of x. So basically this is equal to x minus 3 upon 2, right? So this is equal to pu of x minus 3 upon 2 times du by dx. So basically this is the du is t inverse. So what is the derivative with respect to x is 1 upon 2, right? That's it. This is my distribution. So you can put this, you can put it here. So let's say this my PUU is equal to, how do I define this block function? Let me call it as, it's a unit step function. Let me call it, denote it with the Heaviside step function. Can I call it as h u minus h of u minus 1, something like this? Basically, I'm, instead of confusing you mathematically, this is the concept. That's it. You can define a function like anyways. Okay, so this is my answer. And you can verify it. Let me put the value 3. So it's 3 minus 3 upon 2. So pu of 0, right? Pu of 0 is 1 and into 1 upon 2. So answer is 1 upon 2, right? So at u equal, at x equal to 3, you get 1 upon 2. Similarly, at x equal to 4, you can compute 4 minus 3 upon 2 is 1 upon 2. What is pu of 1 upon 2 is 1. So 1 into 1 upon 2 is 1 upon 2. So this formula works basically. Okay. So you are familiar with now transformations of random variables in 1D, in one dimension, because both your u and x are one dimensional. What happens when you go to higher dimensions? Okay, so before we go to higher dimensions, let me also give you an intuitive understanding of the concept of probability mass. So you see, your probability mass is concentrated in 0 to 1, right? And then this mass, it gets transformed to, it gets spread out between 3 to 5. So there is a shifting and a scaling, right? Imagine this is like some mass, probability mass, and this gets squeezed and it spreads out like this. Still it is conserved, right? Mass is conserved. It is conserved. It is conserved under T. Even if you apply the transformation T, the probability mass is conserved, but just that it goes in some other areas and fills up those areas, right? This is just an intuitive understanding, nothing mathematical here. Okay, let's come to higher dimensions now, n dimensions. Now what happens? Let's say you have a patch here. Let's say your u is a vector now, u1, u2. So how do you define your probability distribution? Let's say again a uniform distribution between 0 to 1. So your p of u is a vector now, of u vector is equal to, is basically uniform distribution. Right here it is all 1. In this region. And outside this region it is 0. Right? Here it is 0. inside the box and 0 outside the box. And again, the property that your PU, now this du is a volume integration over this entire volume. The entire volume. This is equal to what? This is equal to
1.
Yeah. Yes, 1. So, and this mass is conserved. Again, this probability mass is conserved if you apply some transformation. Let's do that. Let's do that. There is some transformation T which converts it into X. Now what happens? Let's say I will not again do it. It's but same exercise. I can shift it. I can rotate it. I can move it to some other shape. Right? This is my X1. This is my X2. And again, my probability mass will be conserved. Right? But this transformation T will just move it to some other area, some other locations. It could also be split, right? It could be made into 2 of these, right? So basically, any kind of, but yeah. So we are interested in invertible transformations. Invertible transformations means T inverse is also defined, right? Here. If T inverse is not defined, then what will happen? Yes. If T is not invertible, then what will happen? Yes. If T is not invertible, then what will happen? You have seen this in the past, in the previous lecture. Yes. Okay, maybe you need a figure to recall. Let's say my T is something like this. I have.
We might have two values of probability.
Yes, yes. Let's say you have something like this, and X is equal to PU. Then let's say my X is this. Then my PXX will be equal to what? It will come from this mass and this mass. Let's say, let me call it U1 and U2. I will not confuse you with U1, U2. Maybe U and minus U. Okay. Then Px will be equal to Pu at under root of X. Oh, let me take it as X, U square. Transformation is not invertible. So this will be equal to Pu of under root X times the derivative. What is the derivative? 1 upon 2 root X, right? Oops, my pen is giving me trouble. Plus Pu at minus under root X. Right? I go to this range and then 1 upon 2 root X. And since there is a mod here, so it stays under root X only. There is no negative sign here. So in this way, we derive the PDF when the transformation is not invertible. Basically, you get a summation term over multiple probability values. But anyways, this is not our concern. In this lecture, we are looking at only invertible transformations. We are interested in T is invertible. Okay. Is this clear? Now, what is PXX? This is PUU times derivative of u with respect to x, and these are vectors now, and the mod, right? And you compute it at u equal to x inverse, or basically t inverse x. Right? Right? Does that make sense?
Yes.
Now, what is this term? This term is very strange. How do you differentiate vector with respect to vector? It's called a, yes, it's called a Jacobian. It's called a Jacobian, and you take the determinant of the Jacobian, and then the mod is anyways there. Jacobian of T inverse. So this term is basically the Jacobian of T inverse. It can also be written as this can also be, this is also equal to 1 upon determinant of Jacobian of T at U. Does that make sense? If you want to read more about it, you can read the calculus. It's basic calculus. When you do integration, the change of variables in your integration, right? Then you will, let's say you are doing the change of variable, then this term, it transforms like this. It becomes d of x times the mod determinant of Jacobian. Here, Jacobian is with respect to, I think, I forgot whether it is T inverse or T. Oh, basically it should be equal to du upon dx. So basically T inverse, yes. This comes from basic calculus, vector calculus, or so basically where you see how the area transforms. Like this du is basically an area, right? An infinitesimal area. And when you transform it to dx, the area transforms like this. This is just like here, you see what is my derivative. It's basically the slope, right? Slope means if your u is this much, how is your x, right? If your u is small, x is large, this means your derivative is large. If your delta u is very large, x is very small, this means your derivative is very small. So it's a measure of how much stretching or shrinking you are doing. So similarly here, this is the notion of stretching or shrinking. Or shrinking. Right? Does that make sense? Are these formulas clear to you? Feel free to ask any questions if they are not clear. So basically we have derived some very important formula here. One is this one. Okay, let me write them down again. So what we have derived here is Pxx is basically equal to Puu, these are the vectors, times absolute value of determinant Jacobian T inverse x, right? Where here the u should be equal to T inverse x. And this thing is also equal to PUU determine 1 upon determinant. Okay, let me put determinant JTU, and this is 1 upon, so I'll just put an inverse sign here on top, right? And again, this is computed at U equal to T inverse X. Does that make sense? These two are very important formulae which we'll be using in today's lecture. So the question is, this formula is very nice, but can I learn this transformation? Can I derive this transformation given probability of U and probability of X? If these probabilities are given to me, or these samples are given to me, samples from U and samples of X, can I derive a transformation? Basically, it's like a trainable model which I can train to map one distribution to another distribution. That's the question. So what's the use? What's the utility? Utility could be that it may be very difficult to sample from the target distribution, the X distribution. It may be this distribution will be difficult to sample from. So what we do is we sample in this distribution, which may be very easy, could be uniform or simple, normal, very simple distribution. And I apply a transformation T and convert this into a very complicated distribution, which is not very easy to sample from directly, right? So using this method that I sample from here, apply the transformation, I can obtain the samples from this target distribution, right? So that's what my goal is. So my goal is given a complicated distribution P X X, which is difficult to sample from. Complicated here means difficult to sample. Okay. Just a minute. Given either this or samples X, just samples X. For example, images are given, faces are given. Let's say faces of some person. Just the samples are given, right? Given a complicated or difficult to sample this or this, can you find a way to sample PX X efficiently? So our solution is take a simple, which means easy to sample, take a simple PUU and learn a transformation T such that X equal to T of U, no, yeah, I think that's it. Learn a T such that X equal to T of U. That's it. So basically, you sample from this easy distribution and transform them, and it's as good as sampling the difficult distribution, the complicated distribution, right? So I will give some examples here. For example, let's say you want to sample from a complicated distribution, could be maybe circles. Something like this. Here. This is your target distribution. It's very difficult to sample from, let's say. Or you are given a Gaussian mixture model. Gaussian mixture model is not difficult to sample from, but I'm just giving an example. Let's say you're given a Gaussian mixture model and you want to sample from here. Or you are given high dimensional, means it could be not just 2 dimensions, it could be high dimensional distribution also, where let's say you have some very complicated shape. Some very complicated shape is there, and you want to sample from this distribution, right? In practice, you could have images. Let's say you have a person versus a house, and you want to sample, and you want to generate. I've asked you, can you generate more samples of a person? Can you generate more samples of a house? Let's say, or I can ask you, okay, this person looks like this today. How will this person look after maybe 10 years? I mean, so this is like a probability of that person given t equal to 10 years. And you have, p of x given t equal to 1 year or 0 today. I'm not doing transformation. This is not a transformation. So yeah, basically you can use it to estimate any distribution, which could be difficult to sample from, but in this way you can proceed. Okay, let's now go on. As the course will proceed, I will give you more and more examples at how in real life this becomes so important. But let's see how to do it. Okay, so the concept is very simple. All of you know neural networks. I'm assuming you know neural networks. In neural networks, how do you train a network? Or T is a transformation, right? So a neural network is also a transformation, right? Which transforms some input. Let me use the notation X. It transforms it into Y, right? This is some neural network. So how do you train a neural network? Yes. How do you train a neural network? Anybody?
We use a loss function to optimize the
Very
values.
good. So number 1, you define a loss function. Theta is the network parameters. Theta. Define a loss function, which is a function of theta. It should be differentiable, right? Differentiable. Okay, then what do you do?
Perform optimization like gradient descent or
Yeah, some gradient based optimization. To find optimal theta. That's it, right? So that's how you do. So can we do something similar here? can we do something similar here? Can I use something similar here when I want to define a transformation T from U to X? These X are not same, just don't confuse. This is some U, this is some X. And I want to find some T, but this T should be invertible. Invertible, and it should also be differentiable, right? So that you can do the gradient based optimization. Okay. For your ease, I have taken an example T, an example of T. Which satisfies both these properties, invertibility and differentiability. Okay, tell me a simple invertible function you can think of.
Identity.
Identity, yes. Okay, something more complicated. That was
AX plus B.
AX plus B, very good. So a straight line basically, right? Or a hyperplane, right? Let's take a straight line. A straight line is an invertible function. So let me define a straight line. How do? I will say X is equal to some AU plus B, right? And here A and B are parameters, right? So this is an invertible function, and this is also a differentiable function. And if you apply this transformation, how will your Px change? Let's say you have some PUU. Let's say PUU is given to you. Now, what will be your Pxx in terms of PUU? Times
1 over A.
1 over A, yes. Basically, du upon dx, or basically 1 upon dx upon du, which is 1 upon, actually it's mod A, right? Don't make this mistake. It should be mod A because A can be negative also, but your P cannot be negative. Right? So this is the answer. Okay. So it's a very simple differentiable. It is differentiable, right? It is invertible also. It is differentiable with respect to parameters A and B, and it's invertible also. So this is an example of T. Now let's go to higher dimensions. This was for scalar, for 1D. Now what about differentiable function?
AX plus BY plus C.
Yeah, so basically you have to say my x1 is equal to something and x2 equal to something. So x1 is a function of u1, u2. Basically my x1, x2 is some p of u1, u2, right? This is my two-dimensional. So what is my x1 is equal to? Okay, so let's take a simple thing. Let's say if I take my x1 is equal to some a times u1 plus b times u2, and x2 is equal to some a times some c times u1 plus some d times u2, right? Is it invertible? Is it invertible?
The
Yes.
matrix A, B, C, D, that should be invertible. Then it will.
Yeah. What is the condition for that?
AD minus BC not equal to 0.
Okay, so we have this condition. AD minus BC should not be equal to 0. That is is called determinant should not be equal to 0, right? Determinant, right? Kramer's rule. Okay. Okay, if this condition is satisfied, then this is invertible. Now tell me, what is Pxx in terms of PUU? Here, I think we also have to put U is equal to what? U is equal to X minus B upon A. Okay. Yeah, what is PU? What is Pxx in terms of PUU? Times the Jacobian. Let's take what notation we use. Determinant of JT inverse X, or 1 upon determinant of JT. Right? This was the formula where U equal to T inverse X. Okay, now tell me, what is this determinant of JTU? What is the determinant of JTU? Okay, let's compute it. So my JTU is equal to dou x1 upon dou u1, dou x1 upon dou u2, dou x2 upon dou u1, and dou x2 upon dou u2. And this is my determinant, sorry, Jacobian. So what is this? This is equal to what? What is it? Right? Is that correct?
Yes.
Yeah, thank you. So in this way, then determinant is equal to mod of AD minus BC. So basically, mod of determinant of JTU. This is equal to AD minus BC. Okay, now that's it. So this is a good way. Using this, I can optimize my ADBC. Okay, no, I have not defined how to optimize them, but at least, okay, this is a transformation which is invertible, and also it is differentiable with respect to the parameters, right?
So, sir, basically, when we are learning the transformation, we are trying to learn the matrix, transformation matrix.
Yes.
That will be the task for the machine learning system.
Yeah, we have to learn the transformation.
Okay.
Yes. Okay, but see, this matrix, this transformation is a linear transformation. Can we do non-linear transformations now? Because linear transformation, what can it do? It can just, what do you say? It can scale your function, scale your probability mass thing, and it can just linearly, right? For example, if this was your input block, it can be transformed in some linear ways. That's it. But you cannot obtain a distribution, let's say, of this shape. Can you ever obtain? You can go from here to here, but can you go from here to here? A very non-linear kind of transformation. Is it possible?
Not using linear transformations.
Yeah, no. So our T has to be some non-linear form. T must have some non-linear form, but then it should be invertible. Okay, it should be non-linear. It should be invertible. It should be differentiable. And also there is this term, as the size of U increases and the size of X increases, this determinant becomes increasingly complicated to compute. So, okay, number one, my T should be invertible. T should be differentiable. And second, and another requirement is that Jacobian, this determinant of Jacobian. Mod determinant of Jacobian should be computationally tractable or computationally easy to compute. Computationally easy. It should be easy to compute. Otherwise, as your x and u become larger and larger, your determinant of J will become overly complicated to compute. And then this condition which you had here of invertibility, this also may be difficult to hold, right? If your Jacobian becomes too complicated. So these are the constraints. So there is one mapping defined like this. I will define it for a non-linear transformation. I will define it for 2D, but it can be extended to higher dimensions also without much difficulty. So how I will do it is, so pay attention here. I will define, I want to go from U to X, right? Where U is a vector, X is a vector. So I will say, let's say my X1 is equal to U1. That's it. And my X2 now is U2 times some scaling factor, which is a function of, let's say U1 plus some shift factor or bias factor, which is again a function of U1. Let me call it as right. So this was like your A and B earlier, the shift and no, not exactly A and B, but this is just a stretching term. This is a shift term. So this transformation, is this transformation linear? This could be nonlinear functions. This could be nonlinear function. Both of them could be nonlinear functions. And maybe they could be a neural network or something, right? Which just take a U1 as input and gives sigma to U1 as output. This could be a neural network. Similarly, this one here, it takes U1 as input and gives mu to U1 as output. This could be a neural network, and this could be any nonlinear mapping basically, right? So in this way, now this T is a nonlinear mapping, right? Operating upon X. Now let's see if it satisfies those properties. Number one, invertibility. Is it invertible? Is it invertible? Let's compute. Given, which means given X1, X2, can you compute U1, U2? What is U1? What is U1? Yes?
X1.
Simply X1, because from here, very easy. What is U2? What is U2?
X2 minus mu2 X1 divided by sigma 2 X1.
X2 minus mu2
X1.
X1. Yeah, because U1 and X1 are same. So you can replace U1 with X1 divided by
Sigma 2 X1.
sigma 2 X1. Very clever. It's invertible, right? So it satisfies the invertibility condition. Is it differentiable? Differentiable with respect to parameters. What are the parameters here? You can say sigma and mu are the parameters, but sigma is itself a neural network. It has got many weights inside. And mu2 is also a neural network. It has got weights inside. Now this whole function is differentiable, and within this neural network is differentiable with respect to the weights. So the whole thing is differentiable, right? So it is differentiable. Let's come to the third condition. What about the Jacobian? Determinant of J, JT, whatever. Is it easy to compute? Can you compute what is the Jacobian? The Jacobian JT, right? So JT is basically dou x upon dou u. Right? What is this? Dou x upon dou u, tell me. So dx1 upon dou u1, dou x1 upon dou u2, right? And dou x2 upon dou u1, dou x2 upon dou u2. What is this? What is dou x1 upon dou u1?
1.
1. Very good. What is dou x1 upon dou u2?
0.
0. Very good. What is dou x2 upon dou u1? Sorry. Dou x2 upon dou u1.
It's
Sorry.
it's some kind of derivative of the neural networks, sigma 2, dou sigma 2 by dou u1 plus dou mu 2 by dou u1.
Yeah, let's write that beast. U1 times some derivative of sigma
U2 times.
So u2.
u2. Okay. Okay, u2 times derivative with respect. U2 times, and here this term is mu, right? No, plus dou mu of u1 on dou u1. Okay, this was a, and what's the next term? Dou x2 upon dou u2.
It'll be sigma 2 sigma 2 u1.
Simply sigma 2 u1. Okay, it looks like a complicated term. Now, what is the determinant of this thing?
Sigma 2u.
Sigma 2 u1.
So it's 1 into sigma 2 u1. It's a very simple thing, right? So easy to compute. So why this is so easy to compute? Because this matrix has a property. What is that property?
It's a lower triangle.
Yeah, it's a lower triangular matrix. It's a lower triangular matrix. That's why it has, that's why the Jacobian is so easy to compute. It is just the product of the diagonals. So we don't need to care about this term at all, right? So this is a property. It's called it's a lower triangular matrix. And why this is possible? Because my each term is progressively dependent only on the past term. So okay, let's say here. So x1 depends on u1 or previous terms. If there were u0s, u etc. those things. X2 depends on u2 directly, linearly, and other terms non-linearly. Let's say u1, u0, whatever. This all dependence could be non-linear. If we had an x3, how shall we define that? X3 is equal to, let's say if you want to maintain these kind of properties, invertibility, differentiability, and mod determinant of the Jacobian should be easy to compute. How should we define our X3 then? Yes, X3 is U3 times sigma 3 of U1 comma U2 plus some mu3 of U1 comma U2. And here these are neural networks again, right? It's a neural network where input is U1 and U2 and the output is sigma 3 and mu3. Basically, there are two networks, or you can say single network with some shared layers. And it estimates sigma 3 and mu3. This will maintain that property that you are. Now, what will be the determinant of Jacobian here with this thing? Yes. What is your determinant Jacobian?
Sigma 2 into sigma 3.
Yes, this will be equal to mod of sigma 2, which is basically of U1, right? Times sigma 3, which is a function of U1 and U2. That's it. So this is a method to construct a transformation which is invertible, differentiable, and also the determinant of the Jacobian is very easy to compute, right? So it satisfies all these three properties very nicely. These are important properties which it satisfies. All right. So technically, this transformation is known as real non-volume preserving transformation or flow. Flow means a transformation basically. Why is it called a flow? Because there is a flow of probability mass. Your probability mass is getting squeezed from one, remember this, probability mass is getting squeezed from one area to another area. So you can say my probability mass is flowing. So my mass is flowing from here to here, some parts from here to here. So it's flowing. Right? My P mass is flowing. So this transformation is called a flow to say that so it has those properties where probability mass is flowing from one region to another region. Just a name called flow. So real non-volume preserving flow. Okay, so this is the transformation. It has these good qualities. Now the question is, how do I train the parameters, right?
Why it is called as non-volume?
Non-volume preserving, because, okay, good question.
So because the transformations are non-linear, so the shape might.
Yeah. So what happens here is let's say I start from uniform distribution, right? And I am doing if my transformation were just transformation of U is some U plus some mu, then my volume is kind of preserved. But if I'm multiplying with sigma, then I'm also scaling it up. So because of the scaling, this volume, which was earlier 1, this is not preserved. Of course, the probability mass is preserved, but the volume is not preserved because of this transformation sigma. So this sigma term makes it non-volume preserving. Anyways, so just ignore this term for now, because to be able to talk about non-volume preserving flows, you have to know what are volume preserving flows, and I'm not doing that right now. So just suffice it to say this is some name, and if you see it in future, you should not be confused. And if you want to read more about this, then this is the area, this is the place where you should read RNVP. Just a name for now. Maybe we will come back to these terms later when we see other possibilities. Okay, let's come to now, how do we train them?
Sir,
Yes.
sir, I have a question. Sir, so we are establishing a certain hierarchy in the dependence of the variables, right? So that x1 depends, x1 it transforms to u1, and x1, x2 transform depends upon x2 and u1 and u2 both. And if there is an x3, it depends upon u1, u2, and u3 as well.
Yes.
So apart from getting a triangular matrix, upper or lower, is there any specific reason, or does it have any other favorable properties?
Okay, so you're asking that we are establishing a kind of order in x1, x2, x3.
Yeah, yes, sir, yes.
Okay, very good question. It's a very good question, I think, which is very well asked. So there is a trick you can do. The trick is like this. You start with some u1 and some u2. You apply this transformation on top of it, this RNVP thing, where your output is x1, x2. And here the problem is that x1 will be same as u1, right? Because of the nature of t. So x1 has not changed. So what will you do? You will flip them. x2 here, x1 here. And then again pass it through some other t dash. And you obtain some value here, let's say x2 dash and x1 dash, right? And again flip it. And you will get some x1 dash and x2 dash. So both of these are RNVP. But what you have obtained here essentially is your x1 dash is no longer same as u1. It's a new value, and this one also is a new value. So for this RNVP, you had given some precedence to this x2, but here you reverse the things and you get both the things as new things now. So basically you are able to update both x1 and x2. So, and you can apply this serially over and over again, no problem. Let's say you start with some particular u vector, you apply some t, then you again apply some t dash, and those flips, etc., could be a part of t dash assimilate inside. Some t double dash, some t triple dash, and you can keep applying it just like layers of neural network. And you apply some, finally some t n dash, and then you will get some x. So these are a series of transformations. A series of transformations. Just like you have a deep neural network where you apply a series of layers, this is a kind of series of flows. Does that make sense?
Yes, sir.
Okay. And still the question which you asked, that there is some order in x1, x2, x3, etc. The answer is yes, true. There, in one transformation, you assume an order, and that's why these flows are also called as autoregressive flows. Autoregressive because they are, let's say, if you go back to this, you are estimating some x1, and then you are using this x1 to estimate the value of x2. And then you use the value of x1 and x2 to estimate the value of x3. So there is a nature of autoregressiveness in this whole thing, right? So they are kind of autoregressive. This is the nature of the flow. Okay, but that is required for the lower triangular property of the Jacobian. Okay. Does
Yes,
that
sir.
make sense?
Yes,
Okay.
sir. Yes, sir.
Thank you. So let's now come to the training part. How will we train our transformations? For training, let's define the loss function. For loss function, you need, okay, what is the goal here? What is the goal? Let's go back to the goal statement. What's the goal? What's the goal?
To learn a transformation that maps simple probability distribution to a complex one.
Yes, very good. So what should be our loss function?
KL divergence or something that matches probabilities.
So we want that our P x, which is basically from the flow, let me write it like this, Pxx, comma theta. Theta are the flow parameters, right? The neural networks, etc. Whatever learnable parameters are here. Theta are the flow parameters. So this estimate should match what? What? Pxx. Let's call it as star. Some target distribution. This is some target distribution. So,
Excuse me, sir.
yes.
Wouldn't we start from PUU, comma theta?
PUU is already given to you, right? You assumed it as a known form.
Okay.
Okay, this is derived from PUU, right? You have some PUU and you transform your U using some T to X and you obtained this. So this is a parametric form, right? Where theta are the parameters. And you want this distribution should match this distribution, target distribution.
So just to be clear, theta are the parameters of T, right?
Yes.
Okay, thank you, sir.
Okay, good question asked. We can also do it. We can also make it a little bit like this. So theta are the parameters and they can consist of two kinds of parameters, phi and psi. What are phi? Phi are the parameters of T. So basically these are parameters of T. So when I say my X is equal to TU, I can say my X is equal to T of U, comma phi. Does that make sense? Where phi are the parameters of T. Oh, let me put it like a semicolon so that you are clear that these are the parameters, right? And this psi
Yes, sir.
can be parameters of U. Let's say I want to keep my U also a trainable distribution. Let's say this is a Gaussian distribution and I want to keep this psi also as the mean and variance, which are also trainable now. So this psi can be here. Doesn't matter because it's a differentiable function. So as long as they are differentiable, my gradient descent algorithm can optimize them.
So like with respect to the previous example, the parameters theta, which is basically the phi, are
Yes.
they the parameters of the neural network functions sigma and mu that were in
Yes.
the previous example?
Yeah, in this case, my theta or my phi was function. Where is my neural network? Yeah, this neural network. So these will be phi. So both these basically they will be phi. This will be the parameters are phi, the weights of this network.
Okay. And like, what is the need to train the mu? We already know the distribution of the mu. So why we are training it again with respect to the psi parameters that you mentioned?
Okay, yeah, it's not necessary to train it. It's not necessary. But yeah, I mean, in case you want to have it, then you can still have it. It's not necessary to have it.
Okay. Okay.
Let's say you are using a Gaussian distribution and you want to instead of putting the load of stretching on T, you are letting the distribution itself to stretch beforehand. That's also possible. Okay, so not necessary, but okay, now let's see, how do you match two distributions? How will you match two distributions? There are different things that you can use, like somebody mentioned KL divergence. What else? Yes. Cross entropy. Yes. And there are other kind of divergences also defined, but they are mathematically well defined, but computationally maybe a little complicated. So we will not do it that way. But let's start with KL divergence. Let's define our loss function, L theta, as the KL divergence between what? The KL divergence between P star X, let me call it as D, the KL divergence between P star X and P X X. All right. This is very easy. Now tell me the formula of KL divergence. Okay, let's say the KL divergence between P and Q, Px and Qx basically, is given by what? Px and Qx is given by yes, integration over x. This is one dimensional. Yes. Yes.
Ex into log of px upon qx.
Px log of px upon qx dx. Okay, yeah, that's the thing. And if you go to higher dimensions, when x becomes a vector, then this becomes a complicated thing. Means you have to say over x. Still remains the same thing. And here it becomes a d of x vector, and which is actually a dx1 times dx2 times dx3, etc. So there is a simpler way to write it. You write it like this: expectation. See, this term is an expectation term, right? You know, whenever you are multiplying px with a function of x, then this thing is an expectation of that thing, right? Are you familiar with this? This is just by definition. expectation. It's an expected value. Just a way of writing. So what is the advantage of doing it? First of all, the notation becomes simpler. You don't have to write integration everywhere. And just that keep in mind that this px comes here. And then this term comes as it is here. And you are saved off the effort for writing integration, dx, etc. And also another advantage is that it works for both continuous random variable as well as discrete random variable. If it's a discrete random variable, you have to write it as a summation term. But this notation is common, so you don't have to worry about whether x is discrete or continuous, and you can just use this form. Okay, so let's use this notation. Right, this was just a separate thing. So this is equal to, so I have to write x is sampled from the first term. So this is expectation. X is sampled from p star x. X is a vector. Right? And expectation of what? Log of px minus log of qx, right? So I will write it like this. Log of p star x minus log of p x. Does that make sense? Now you want to optimize your loss function with respect to theta, but this is not a function of theta, right? This is some constant term. Constant with respect to theta, right? Only the other term is a function of theta. Now let's see what is the other term. What is this term? Okay, can we expand it in terms of the transformation where theta actually will appear? So this thing is equal to, use your formula, which we wrote here. This one, pxx can be expanded in this way. Okay. So this thing is equal to puu. And in case you have some psi, you can put it here. If you don't have it, no problem. Times mod determinant of j of T inverse, right? X comma, basically this phi, right? Did I do some mistake in writing this, or is it correct? Okay, this is equal to expectation x is sampled from p star x and then you have this term. This is the constant term. I will throw it away. Negative sign comes out. Minus log of pu u comma phi, sorry, psi minus or plus log of, this minus sign has come out, log of mod of determinant of j T inverse x comma phi. Okay, now what is my u here? Everything is in terms of x and I'm sampling x. So I have to compute u by inverse transformation, right? So I will replace this u by T inverse of x. Right, so my u is basically T inverse of x. Now everything is in terms of x. Now This is my final form. This is my loss function where I know everything. I'm sampling X, and using this X, I'm computing T inverse, and using, I know PU, the formula I already know. It could be a uniform distribution or a Gaussian distribution. I know this value. And now here, I know X. I know the Jacobian thing. Determinant of Jacobian was, if you remember in RNBP, it was simply the product of sigmas, and it was very easy to compute. Take the log, and that's it. So you know every term in this matrix. Now the problem is you have got expectation, which is an integration. Integral over some very large volume. How will you compute this? How will you compute expectation? How will you integrate this thing over such a large volume? Yes?
We'll just take an approximation instead by sampling.
Yes, very good. So it's called Monte Carlo approximation. Let's discuss briefly what is Monte Carlo approximation. So in general, Monte Carlo approximation is this: expectation value over when X is sampled from some Px, some Fx. This is equal to what? Let's say you obtain n number of samples, xi, I goes from 1 to n. So you will compute f xi, sum over all I equal to 1 to capital N, or 0 to n minus 1, whatever you want to call it, times 1 upon n. And these xi are samples from pi, from px basically. This is Monte Carlo approximation, and this is valid for in general. This is valid in general, not just for the flows, but in general. Monte Carlo approximation says whenever you want to find out expected value of any function over x, where x are samples from a given distribution, then you just get those samples and find out this average value, and this should be good enough to estimate your the integral, which is a very complicated thing. Right? Let me write it down here. So this thing is basically equal to integration of fx pxx dx, integral over all the entire x basically. And if x is a volume, if x is a vector, then this becomes more complicated to compute. But this thing still says the same. This thing is still the same. And you'll be happy to know how many samples do we need in general to estimate this. How many samples do we need? Okay, does it become okay? If let's say if my x is multidimensional, x is very large in dimensions, let's say 100 dimensions, 500, 1000 dimensions, million dimensions, does the number of samples required to estimate this term also scales up? The answer is no. It does not scale up. So generally 20 to 30 samples are sufficient to compute this whole thing. Generally 20 to 30 are sufficient. Of course, if your PDF is very, very complicated, then you may need some more, but in general, they are sufficient. So, okay, so let's come back to this part. So how do you estimate? Okay, it's already time now. Let me, let's meet on Wednesday again, and then we will pick up from here. All right. All right.
Excuse me, sir.
Yes.
So just the last point. So n would approximately depend on the complexity of P star x.
Yeah, but generally it turns out that 20-30 samples are sufficient to estimate the Monte Carlo approximation. Of course, here we are doing the gradients and also we may need more samples, but in general, this one is sufficient.
Okay. Okay. Thank you, sir.
For training, yes, we will be needing more samples. But to estimate just this term, it is sufficient. Okay, thank you very much. So we'll meet again on Wednesday evening. Bye. Thank you.